Okay, folks, so let's keep working on this. I'm just going to run through a series of examples. The ones that I'm choosing to do are ones that I've found a little bit more challenging than other U-substitution problems, and so I'm just trying to show you some of the tricks of the trade, if you will. So first of all, let's go ahead and rewrite this problem here. I don't know why math people do this. It's sort of show-off-ski on their part. Really, this is this integral right here. This sort of looks like the expression 1 over x, but there's been some shifting going on. Okay? So in this case, what I'm going to do is I'm going to let u equal 5 minus 3x. That would make du equal to negative 3x, negative 3 dx, differential x. So I look up above and I notice, okay, I'll be replacing this expression right here with a u, and I've got a dx factor, as I've been showing. So we've got this dx factor here, this dx factor here, but I don't have a minus 3 factor just sitting around on its own. So let's divide this minus 3 over to the other side. So this gives us minus 1/3 du is equal to just differential x. So now we're ready to do the substitution. And in place of the 5 minus 3x, we will have 1 over u. And then in place of the differential x, we're going to put minus 1/3 du. Okay. I'm going to go ahead and factor that minus 1/3 out. So we're left with this integral here, which you can see, that should be a du. And I think you can see the point of this u substitution. This is much easier to work with now. Here I'm just saying what function, when we take its derivative, gives us 1 over u, and the answer is the natural log of the absolute value of u plus some constant. So now all we need to do is to do the back substitution step, and for that we'll say that what was u? Well, u was the expression 5 minus 3x, so we end up with minus 1/3 times the natural log of the absolute value of 5 minus 3x plus c. Okay. Oftentimes with trig functions, what you're going to want to do is you're going to want to rewrite them in terms of sine and cosine. Usually we're more comfortable with that. So let's see here. We could rewrite this as the sine of theta divided by the cosine of theta d theta. Now we have a choice here. I see the expression sine theta, and I see its derivative up to a constant showing up in the denominator here. But likewise, I see cosine of theta, and I see cosine's derivative showing up here. So the question is which one should I let u be? Should I let u equal the sine of theta, or should I let u equal the cosine of theta? Okay. So I would encourage you to try this both ways and see which way seems to make your life easier. But I'm going to go ahead and just do it. So I'm going to choose to let u equal the cosine of theta. That makes du equal to minus the sine of theta d theta, or minus du is equal to the sine of theta d theta, where I divided this minus sign over to the other side. So now we can rewrite the original problem as the integral. Well, actually, I should copy this over, so let me do that. Sine theta over cosine theta d theta. So now we're going to do a u substitution on this. And in place of the cosine of theta, we're going to put a u. And in place of the sine theta d theta, we're going to put a minus. So let's go ahead. We could write it many different ways. We'll write a minus du here. So that gives us minus the integral of 1 over u du. Folks, what you do in simplifying and in kind of getting constants factored out of integrals, everyone does that a little bit differently. It's just a simplification procedure. But eventually you should wind up with this integral right here, which, similar to the last example, comes out to be negative natural log absolute value of u plus c. Now we simply need the back substitution step. We get minus the natural log of the absolute value of the sine of theta plus c, because theta was what our original variable was in terms of, and we had to do that back substitution. Folks, I've made a mistake. Sorry about that. I shouldn't have. I wrote this here, and then that's what I looked at. I let u equal the cosine of theta, so that should be cosine of theta. We're just going to go ahead and clean that whole thing up. Equals negative natural log absolute value of the cosine of theta plus c. Okay. So this is a perfectly fine place to park your answer. A lot of times math people, for fun, will write it this way. That's the same thing as the cosine of theta to the -1 power plus c, where what did I do? I brought this negative sign inside the logarithm as a power. Remember, constants go inside logarithms as powers. And then that says 1 over the cosine of theta, but that's just the secant of theta. So a lot of times you'll see actually the antiderivative of the tangent written this way. Math people would argue that's ever so slightly simpler than writing it this way, where you've got the negative out front. Okay, so I'm going to let you do letter G. You try. Okay, so you try letter G. Give that your best shot. It's going to be very similar to letter F, but the substitutions will be different. And now I'd like to move on to a couple of challenging ones. So I'm going to do letter A here, and I'm going to leave you to do letter B. So you try. These are a little bit more challenging substitutions because they're going to require one little extra trick here at the end. Okay. So let's give that a shot here. I see the expression 1 plus x cubed, and that's sitting inside the square root, so I think I might have some trouble with that. Let's let u equal 1 plus x cubed dx. Well, when I find, no dx. When I go to find differential u, I'll find that differential u is equal to 3x squared differential x. Or 1/3 differential u is equal to x squared differential x. But when I look at this, I'm trying to do a u substitution on this. I don't quite have that. Notice I've got an x to the 5th here, not an x squared. Well, what could I do? Well, I could first of all rewrite this problem as x cubed times x squared times the square root of 1 plus x cubed differential x. Now this is just, this is one of those tricks I feel like you need to be shown the first time. Maybe some people find it, they're able to figure it out the first time. But it's helpful to be shown this the first time and then realize, okay, I can maybe do it on other problems. So let's see here. Well, I'm going to put a u here, so we even start on the substitution. I'm going to put a u here, right? And look, here I've got a factor x squared times a factor differential x. So I can replace all of that, this factor differential x, this factor x squared, with 1/3 differential u. Okay, we're sort of seeing, okay, we'll just go ahead and pull that constant out. That's the differential u. But we still have this x cubed yet to account for. What can we do? Well, this is the first time we've done this trick in this class. I'm going to go ahead and actually, even though I let u equal 1 plus x cubed, the consequence of that would be, if I, oh, we're having a doozy of a time today. If I want to go ahead and solve this expression for x cubed, I would get that x cubed is equal to u minus 1. So then this is what I'm going to go ahead and plug in for this x cubed right here. So we get u minus 1. Now you may argue this doesn't look all that much simpler than the original problem, but here's the rub. Originally we had a complicated expression sitting inside of a square root. After we were done with the u substitution, there's nothing complicated inside the square root. Instead, it's a polynomial term out here. Okay? So let's go ahead and finish this out. At this point, we're going to have to use all sorts of tricks. We could rewrite this as the integral of, so let's see here, this would be u minus 1 times u to the 1/2 differential u, or 1/3 integral. Now let's distribute that so that would give me u to the 3/2 minus u to the 1/2 differential u, where that was distributing the u to both those terms. So now we can actually evaluate the antiderivative. Adding 1 to the exponent would give us u to the 5/2 times, and then dividing by the new exponent, 2/5. Minus, and then adding 1 to the exponent gives us u to the 3/2. Dividing by the new exponent gives us 2/3. And then we need our plus c. Okay. We could clean this up some more. I'm not going to worry about it too much. This gives us 2 over 15. But then what was u? Well, u was 1 plus x cubed to the 5/2 power minus 2. We're distributing this 1/3, so this minus 2/9. and then that would be u to the 3/2 power, but again, u is 1 plus x cubed to the 3/2 power plus c. So that's a much more challenging problem than anything we've seen so far. And the idea was we had, okay, a more complicated, we were going to do a u-substitution, but we didn't have the right factors lined up. So in this case, it was advantageous to solve the expression u equals 1 plus x cubed for x cubed because we had that extra factor of x cubed there. So I'll let you try letter B. Sorry, it doesn't look like I gave you quite enough room. So if you need to put on an extra sheet, go ahead and do so. But I'll let you try part B. Oh, and I'm going to have you guys try C and D as well. Are those the same problems? No, they're not. They're different. Good. I'll let you try C and D as well.